only type of extreme weather. Well, hurricanes and tornadoes and severe thunderstorms aren't the only types of extreme weather that we worry about here on Earth. And I'm sure that you're pretty aware of that. There's other types of extreme weather, whether it's droughts or fire weather or major heat waves, that also really do cause tremendous amounts of damage and tremendous amounts of problems here on Earth. And so for this lecture, we're going to talk a little bit about that. So for this lecture, first off, we're going to learn the key ingredients in superstorm formation, and then we're going to talk a little bit about other types of extreme weather. So first off, let's talk about superstorms. So I've mentioned in previous lectures, and really an overarching theme in this course is we live on an unevenly heated Earth. If you think about it, the sun comes in from a high angle at one location, from a low angle in another location. It also heats different surfaces differently, and then you have different specific heats. You have land versus ocean, you have different elevations. All of this results in an unevenly heated Earth. All of this results in an unevenly heated Earth. And weather is one of Mother Nature's attempts at balancing everything out. Now, unfortunately, or I guess fortunately, as long as the sun is out heating our Earth, it's going to heat it unevenly. And the more it heats it unevenly, the longer we're going to have weather. Well, in the case of really major differences, let's suppose you have a really cold continental Arctic air mass next to a really hot maritime tropical air mass. Or what would happen if a hurricane slammed into a nor'easter? Or what would happen if you had some kind of cold air mass that a hurricane ran into? Now you get some of the biggest differences, some of the biggest clashes of weather across the entire world. And this creates superstorms. And so that is what we're going to talk about today. So first off, superstorms occur when the extremes of weather clash. A few good examples of this took place in 1991, and then another one 21 years later in 2012, with the perfect storm and Superstorm Sandy. The perfect storm ended up having a movie named after it, and who knows, maybe someday Sandy will too. Basically what happened is it was fall. There's still plenty of heat and moisture near the equator, so hurricanes were still able to form. But as those hurricanes were traveling north, they were interacting with really cold air masses that were coming down from interior Canada. And instead of weakening, these air masses began to feed off of each other. And they began to dance together. They began to grow together, creating really severe storms. Another good example of this was in 1993 during what was called the Storm of the Century. And in fact, both of these superstorms are going to be subjects of this week's activities. Instead of doing an investigation this week, you're going to be watching two documentaries about these two different superstorms. And the 1993 Storm of the Century ended up being this really incredible superstorm that developed when really cold Arctic air collided with really warm tropical air. So here's an image of Hurricane Sandy, and what we had here was the hurricane off the coast of the Atlantic, and then over here there was this really cold air mass. And so suddenly you had these major differences in temperature. And if you remember from this class, differences in temperature create differences in pressure. Differences in pressure create wind. And so now you get these really strong windstorms that develop. The other thing that happens, though, is a hurricane has a lot of moisture associated with it. And so all of that moisture is now feeding into the frontal boundary between this warm and cold air. And actually, let me draw a front here. So right here, there was a front that developed. And all of that moisture was now being fed into this cold front. And so rainfalls became very intense, winds became very strong, and the two storms hadn't even fully collided yet. Eventually, they did collide. And when they collided, they created tremendous amounts of stormy weather for much of the eastern United States. Now, what was interesting was initially, this wasn't expected to happen. What was initially expected to happen was Superstorm Sandy, or Hurricane Sandy at the time, was expected to make its way north and then off to the east, which is typically what these storms do. However, the high pressure system out here called the Bermuda High that would have normally caused the storm to make that turn was not there. And instead, let me erase this ink. Instead, the storm took this worm-like path where rather than turning out to sea, it made a sudden turn back towards the coast. And it actually rammed right into this jet stream with that associated front. Boom, all of a sudden you have the best of both worlds. Really cold air colliding with really warm air, lots of moisture. Boom, superstorm is born. The same thing happened in 1993 with that storm of the century I talked about. A low pressure system developed over the Gulf of Mexico, and that low pressure system began to push moisture northward towards this Arctic air mass. There's a front between the Arctic air mass and this warm, moist air. That moisture began to rise, that warm, moist air began to rise over the front, and boom, you get this tremendous amount of very stormy weather. And this particular storm actually produced two very different but devastating consequences. Pretty much north of Florida, here across what we call the eastern seaboard, this whole region experienced lots of snow. I'll put a little asterisk up here for snow. That's actually the station model symbol for snow. Terribly drawn asterisk, but this area received lots of snow. Meanwhile, this area down here, pretty much covering the Florida Peninsula, Cuba, and all the way down to the Yucatan Peninsula, and even Central America, this area here received severe thunderstorms. Now I'll try to draw what looks like a terrible lightning bolt. Maybe a little cloud here. But yeah, right here, this area received tremendous thunderstorm activity. And in fact, there were tornadoes that developed there. So this was a very monstrous storm. And like I said, in this week's module, you're going to watch the documentary about this, or one of the documentaries about this. One of the ones I watched growing up that I was really fascinated with. The storm of the century formed because, again, you had really warm, moist air over the Gulf of Mexico and extremely cold Arctic air from the interior United States. This actually killed up to 310 people. I've actually heard some numbers a little bit lower than this. I've heard numbers as low as 270. So this was responsible for killing quite a bit of people. And it kind of sounds somewhat similar to Sandy. Again, you had warm, moist air colliding with very cold, dry air. Warm, moist air colliding with cold, dry air. And then one last example, The Perfect Storm, which again was actually, a movie was made out of this. This actually formed, again, from a cold polar air mass colliding with a hurricane. And this storm eventually grew to intensity where it actually, the low pressure that developed it, or that developed from it, eventually became an unnamed hurricane. It was so strong, and it fed off of that warm, moist air so much that it actually became an unnamed hurricane. Thankfully for the perfect storm, the worst of it was offshore. The areas right along the coast of the northeast where this formed were actually dealing with it, but the worst of it was way offshore. The movie that I talked about was actually based on a ship called the Andrea Gale, a fishing ship that went out. It was the last fishing of the season. They caught all this fish. They were coming back, and they were killed trying to travel through the storm. And the 6 people on board were killed by it. So the 1991 perfect storm looked like this. And again, most of it missed the east coast of the United States, but just the very edge of Massachusetts really experienced some damage from it. But areas off the coast were a lot more devastated. So that's one type of extreme weather, but there's other types of extreme weather we deal with here on Earth, and I'm just going to talk just very briefly about a few of these before we wrap up this module. Some other extreme events: heat waves, droughts, ice storms, fire weather, and again, this is just a few types of extreme weather. So, first type, heat waves. I'm sure you've experienced a heat wave at some point in your life, just a prolonged period of above average temperatures. We get them here in California. They usually only last a few days. For some locations, they can last much longer. But basically what happens with a heat wave is you actually get some kind of persistent, dominant high pressure that stays over a location and just stays parked there. And if you remember, high pressure has sinking air in it. And so there's no clouds. The other thing is, as that air is sinking, it's compressing and it's warming. The last thing is, in areas of high pressure, there's lots of warm air advection from the equator, from the equatorial regions, moving up. Those 3 things combine to create areas of really, really hot temperatures. And these temperatures can last for days or even weeks. One of the worst heat waves on record happened here in Europe. And this actually was responsible for thousands of deaths. This happened in 2003. And as I mentioned, it was responsible for thousands of deaths. But as I just mentioned, these heat waves are caused by these areas of high pressure that just stay in place. Areas of high pressure that just stay in place. And as I mentioned, the 2003 heat wave can create tremendous amounts of problems. Now, the reason why Europe was so impacted is because most of Europe isn't built to handle heat. Most European homes and most European infrastructure is actually built to handle cold. And so many of the features that they have trying to keep them warm during the winter made them sweltering hot during the summertime. So yeah, it was actually a pretty major issue. Now what about droughts? We've experienced droughts here in California quite a bit recently. What actually causes them? Well, you could take whole courses on different causes of droughts. Droughts can actually be caused by a number of different things. I will say the drought that we experienced here in California over the last roughly decade has been caused by this persistent high pressure system that has caused the jet stream to travel up and over the US West Coast. And this jet stream behaves like a freeway for low pressure systems and for their associated mid-latitude cyclones, warm fronts and cold fronts, and all the rainmakers that come with them. Well, when you have a ridge like this that develops, what that actually does is that prevents those storms from hitting your region. And so what we were left with instead was lots of heat and lots of dry weather. Now, with that said, that's not the only cause of droughts. Other causes can deal with things such as increased water usage. A drought in another part of the country can greatly affect how much water you're allocated. So weather isn't the only thing that is an issue here. Other things are also at play. But one of the questions that I use to advertise this course, and one of the things I love to discuss with my classes are droughts the new normal? So what I have in this image here are two different pictures of the same location. The first one is Folsom Lake. Folsom Lake is a lake east of Sacramento, and this was Folsom Lake in July of 2011. This is actually during the dry time of the year, and if you take a look, Folsom Lake looks pretty full. It looks very full. Well, after 3 really dry winters, this was Folsom Lake in 2014, and this was actually in January of 2014 during the wet season. And as you can take a look, Folsom Lake was a lot drier. There's still a few puddles, but I mean, this is way drier than typical Folsom Lake. So this is actually a big issue. This was actually something that was seriously a major problem. But is this our new normal? Well, there's a few things that you have to consider. The first thing, and this is most related to our course, is have weather patterns changed? So I mentioned earlier that we had this big ridge that developed over the west coast of the United States. These ridges are what are called Rossby waves. And what actually is hypothesized right now, and there's still a lot of research being done on this, so we can't necessarily say that this is for sure what is happening, but what we believe is happening is as the Arctic is becoming a lot warmer, that's actually making our jet stream a lot wavier. Normally what happens is in a typical winter, you have very cold air here, lots of warm air down here, and what you end up getting is a relatively straight jet stream dividing the two. Well, what's being hypothesized right now is as the Earth is warming, the Arctic is actually warming up faster than the equator. And this could trigger a wavier jet stream. Now, do we know that for sure? To be honest with you, we don't. But we're still trying to figure it out. So that could be something that may be a new normal for us. So have weather patterns changed? I'm going to say the jury's still out on that, but the ridge pattern that we've had over the last several years has been very persistent. And in fact, I'm recording this in 2018. We just came off of a winter that had a very wavy jet stream, and we had a ridge during most of the year. We had a nice wet March that kind of saved us, but it was looking pretty bad there. But what else has changed? Have populations changed? What this results in is changes in water use. If a city like San Jose has a higher population, that means you now have more people. More people means more drinking water. More drinking water means less water in our reserves. So is that happening? More people also means more bellies to feed. More bellies to feed means more food needs to be grown. More food needs to be grown means more farming. Farming uses up a lot of water. So is that something that we need to be concerned about? And then has land use changed? Have we done things to our water table? Have we done things to our reservoirs? Have we done things that could potentially put us in more droughts in the future? Again, I would say the jury's out on this now, but stay tuned. Let's see what happens in the next few years. I wouldn't be surprised if droughts do end up becoming a new normal. The last thing I'll talk about, or the last two things I'll talk about are ice storms, and then we'll heat things back up again and talk about fire weather. So, ice storms, one of the reasons why I love living in California. So, ice storms occur when there's a lot of precipitation that freezes just before it hits the ground. Typically, freezing rain is what we're talking about here. In order for freezing rain to develop, if you remember from several modules ago when we talked about precipitation, you need an inversion to be present. An inversion is basically a warm layer on top of a cold layer on top of the ground. And this image down here shows this. Let me try to get my cursor to show up here. So a warm layer on top of a cold layer. As snow falls to the ground, it falls through that warm layer. It then melts and then falls to the ground. Now, as it's falling through this cold layer near the ground, it begins to quickly cool to the freezing point. However, if the cold layer is very shallow, it might not fully freeze before it hits the ground. Instead, it'll freeze as it hits the ground. And when that happens, that creates pictures like this one right here, where you can see ice has fallen and you see icicles have formed. This is what we call freezing rain. And so ice storms are storms with a lot of freezing rain. The best way for something like this to form is usually ahead of a warm front, because you get a strong inversion ahead of a warm front. The last thing I'll talk about is fire weather, and this has actually become an issue here in California, especially in this last year. So in 2016 and 2017, we had a lot of rain, and that caused a lot of vegetation to grow. And then in the summer of 2017, we had a lot of heat. It got really hot, it got really dry, and this dry heat began to dry out that vegetation. Well, when you have lots of warm air, that quickly brings ground temperatures close to the ignition point. It brings them close to that temperature that they need to be in order for fire to develop. Well, if the air is also dry, that allows one of two things to happen. First off, that prevents any humidity from quenching the fire. But the other thing, the more important thing, is dry air allows sparks to occur. Have you ever touched a doorknob or anything metallic during a dry day, a really dry day, and feel a shock? Well, dry weather allows sparks to occur. And so now you've got this really hot air and you've got sparks to occur. That can easily trigger combustion. Finally, however, you also need high winds. High winds behave in a way that allows oxygen to feed into the fire. Oxygen is actually fuel to the fire, and it allows the fire to travel very quickly, so it carries the fire. This last year, there was a devastating fire in Santa Rosa, and what made that fire so devastating is that it traveled so fast because of high winds. High winds fueled this fire, fed it with oxygen, and allowed it to travel really fast. There was another fire in Southern California near Ventura that exploded in size because the winds were favorable for it to happen. So we need warm air, dry air, and windy air to form fires. And as droughts are happening more often, we may have to worry about fires more often. that's it for this module. So make sure that you get your module quiz and your activity done watching those 2 documentaries.